specifications. So here we have a few examples. We can see a large automations presence in energy, building, factory, and process automation. However, there are also representatives from very different domains like mining equipment and laboratory and analytical devices. In all, there are over 60 published companion specifications. So what if System Modeler and our digital models also could speak OPC UA? Let's look at some potential applications. So we could do a data collection and analysis. So here, for example, we have a lab scale bioreactor, a device made to support a biologically active process. Maximizing the yield from these kind of processes requires good control over the environment conditions like temperature, pH levels, oxygen levels, and many other parameters. By connecting to it, we can collect the data that is relevant for our particular process and do post-processing in Wolfram language. We can also do various kinds of data analysis or create data-driven models, like, for example, use the data to train a neural network. Which brings us to the next use case, high-level control and user interfaces. So what's the point of training a neural network unless we can put it to good use? So we can take the trained network and import it into System Modeler. With our model running in real time and connected to the system, we can feed sensor data into the neural network and use the output to control the system, thereby running the neural network against the real system in real time. We could also prototype and develop other high-level algorithms for controlling our system and run them in real time against the real system. Another option is to build dashboards and custom operator interfaces using Wolfram language. This can be extremely useful, for example, in lab settings, where we might do a wide variety of different experiments using the same equipment. Then you can build tailor-made control panels that are targeted to the needs for operating and monitoring your specific experiment. Another broad area of applications are digital twins, software in the loop and hardware in the loop simulations. So say we're writing PLC code to control our system, and we want to test that PLC code before deploying it to real hardware. If we have the model of our system running in real time, we can connect that to our PLC simulator. Then we can run the software in the loop simulations and test our PLC code before deploying it to actual hardware. Likewise, when we do deploy our PLC code to real hardware and connect that to our simulation, we can run hardware in the loop simulations, enable us to conduct more tests without access to the real system. If the human-machine interface, the user interface of the system, is connected using OPC UA, we can also connect it to our digital twin instead and do operator training with the real operator environment, or using the real operator environment, which could be a cost-efficient solution since there is no wear and tear on physical equipment and no downtime in production. It also enables safe failure simulations for practicing emergency procedures without risking actual equipment or production. So for connecting System Modeler and System Modeler models to OPC UA servers, we have the Wolfram OPC UA library. It is available to System Modeler users as a free download from our library store. And the library enables real-time data exchange with an OPC UA server by providing components for reading and writing node values. It uses the efficient TCP binary mapping of OPC UA with TCP/IP as the underlying transport protocol and the binary encoding for message content. So it's highly efficient with minimal overhead and low bandwidth usage. It also has support for security features like authentication, message signing, and encryption. So if we look at some of the components in the library, we have at the core of the library, we have the client component. This component represents the connection to the server. So here you can specify connection parameters like the server URL, what authentication to use. It supports username and password-based authentication as well as certificate-based authentication. And you can also configure the security setup where you want to have everything sent in plain text or sign your messages or sign and encrypt everything. All components for reading and writing data must have access to the connection to the server, so they need to be connected to a client. And the client is also used to distribute the clock signal that triggers the read and write request. So we connect the clocks that define these clock signals that are then distributed to the connected read and write blocks. It is, of course, possible to have several instances of the client component, so you can connect to multiple OPC UA servers from the same model if that is required. OPC UA uses X509 certificates for secure communication and enabling encryption, authentication, and trust between clients and servers. That is likewise most commonly known HTTPS as well uses the same kind of certificates. So it's a well-established technology. Each of the OPC UA applications, server and client, has one application instance certificate. There are two major ways to manage your certificate. One can have self-signed certificates, or one can have certificates that are signed by a certificate authority. So with self-signed certificates, they are generated by each OPC UA application, the server client. And the trust is explicitly configured, meaning each application must manually trust the other's certificate. And this becomes quite cumbersome in large systems when you have many clients and many servers. So all clients need to be configured to trust all the servers that they need to communicate with. And all the servers need to be configured to trust all the clients that wants to communicate with them. On top of that, certificates usually have an expiration date, so it becomes difficult to manage in large systems. A better option then is to use a certificate authority. So one have certificates that are issued by one trusted certificate authority that establishes a chain of trust. So the trust is implicit. Each application trusts the certificate authority, and therefore any certificates signed by the CA, which makes it a lot easier to manage in larger systems. So there are specific components for reading and making read and write requests, and they are available in variations for working with values of type real, integer, and Boolean in the shapes of scalars and 1D arrays and two-dimensional arrays. Common for all the read and write components is that they have parameters for specifying which node ID to read from or write to. And as I mentioned before, they must also be connected to a client block for getting the connection to the server. In OPC UA, nodes are identified by either a numeric integer ID or a string identifier. One thing is that OPC UA has a richer list of types than Modelica that is used in System Modeler. So for example, it has unsigned and signed integer in all combinations of the usual width variants, whereas in Modelica we only have one basic integer. So when writing data, we must also specify the specific OPC UA data type that should be used for the write request. So how does this scale if we increase the number of nodes that we want to write data to? So when we connect the write component to the client, all those writes are aggregated into one write request, meaning the overhead of adding an additional node to write to is minimal overhead. So it's fairly efficient. And the same holds for all the read requests. And so all the reads are aggregated into one single read request. That is executed with the clock frequency defined by the clocks connected to the client. In some cases, you might want to sample different nodes at different rates for various reasons, and there are special components in the library for facilitating that use case as well. So let's move on to error handling. In OPC UA, status codes are used for indicating the state of a request and the quality and state of a data value. So status codes comes in 3 different severity levels. They can be good, uncertain, or bad. And they can also carry additional information about the reason why the status isn't good. For example, maybe the value is at the limit of the sensor operating range, or the communication with the data source has failed. So all the components for reading and writing values have one extra output, which is the severity of its current status. They also have a parameter to control the block's built-in error handling, where the possible choices are error on status severity uncertain and bad, which means the simulation is aborted as soon as something isn't good. Or we could have error on status severity bad, which means the simulation continues with uncertain values, but aborts when we have bad values. Or we could simply do reporting of status changes, so the simulation continues regardless of the status. So selecting any of the last 2 options mean that we could do error handling in the model. Maybe the bad value isn't that important to our operation, or we can shift to a different operating mode to remedy the situation. To aid in the decision making, the components also come with timestamp outputs, so that it's possible to take different action depending on how long the value has had the current status code. Another effect of selecting to only report status changes is that the simulation will automatically reconnect to the server in case of the connection goes down due to network issues as well. So let's jump into System Modeler and do a quick demo of the library. So this is System Modeler, and here to the left we have the class browser that shows the loaded model libraries that we have. And here we have the OPC UA library loaded. Included in the library are several examples that we see here that illustrates different concepts used in the library and different usage scenarios. To make it easier to get started, the library is shipped is bundled with 2 OPC UA servers. So we don't have any dependency. So the examples doesn't have any dependency on an external OPC UA server. So the first one is the example server, which contains nodes of all types that's supported by the library and is used to support the examples provided in the library. But you can also use it for your own experiments. The other server is more configurable. So here you can create the server with a custom list of nodes.
Arthur, can you zoom in a bit?
In the documentation center.
Yes, yes. Yes.
Better?
Yeah, better.
Yep. Yeah, so the var server serves a custom list of variables of type double. So it's real valued nodes only. But you can define your list of nodes yourself and use it for your experiments. So we're going to use that for this demo today. So there is a link that leads to the location on disk where we can find the actual executable for the server, and we have to then go into the actual folder for our current platform. So I will start the server with two variables, one called the ref and one called level. So now I have started that server. Now I have prepared a model of a tank that is controlled by a PI controller that reads its reference value from the OPC UA server and reports the current tank level to the OPC UA server. So we are going to build a small example model that sets that reference value and reads back the resulting tank level from the OPC UA server. So let's create a new model. And zoom in a bit. So the first thing we need is a client that we can drag in here. And in the client, we have various parameters for configuring the connection to the server. So the first most important one is the endpoint URL, which is the URL of the server. The default value will work for my example server here. And here we also have the security configuration. So we could select between unsecured communication, meaning it's not encrypted in any way or not signed, or we can select secure communication and configure it, opening the editor for that. And here we can set up all the various security parameters, like selecting the algorithm for signing and hashing, and the security mode if you want to sign the messages or sign and encrypt and so on. And there are options for whether you are using self-signed certificates or a CS-signed certificates. In this example, though, the server doesn't have any security enabled, so we need to have it in unsecured. So the next thing we need is to define our clocks for reading and writing. And for that, we're using the standard library components in clocked and clock signals, where we have a periodic exact clock that we're going to use. So we will use the same clock for reading and writing. So I will connect that to both the clock inputs of the of the client. And we will set the clock rate to 10 milliseconds. So next, we wanted to write to our server. So we go to the OPC UA library, and in components, we can find, if we dig down, a subpackage with the components for real signals. So it's organized by the type. So we have real signals, integer signals, and Boolean signals. So we're going to drag out the scalar write block, which we will rename to write ref, so we recognize it. And we will connect that to the client. So we need to configure our write block. So first of all, we need to select the type of the variable that we are writing to. And as I mentioned before, the types in this bundle server is only serving double values. So we will select double. And it uses, then we will specify the node identifier, pointing out the exact node that we want to write to. And first we need to specify what type of ID we are going to use. And this bar server uses string IDs. And we named the variable ref for the reference value for the controller. Then we also need to specify a node namespace. Usually that is for all the local server nodes, that is 1. So that is correct in this case as well. So there we have our write block. Now we need to provide some signal to write as a reference signal for the controller. And for that, we will use a signal source from the standard library in the blocks package. And there we have sources, and we will use a pulse source for this. So something is happening. We'll connect that to our write component and set some parameters. So I want the amplitude of the pulses to be 0.25, and the period we can set to 20 seconds. And let's set the offset to 0.25. So we will get the pulse train alternating between 0.5 and 0.25. Next, let's read the level that the current level that the simulated plant model publishes to the OPC UA server. And for that, we will use a read block, of course, reading one scalar real signal. And we start by renaming it to read level so we can recognize it. And connect it to the client. Next, we need to, so here is a difference between the read and write, or one difference between the read and write block. When we write, we need to specify the type for writing, but reading, that is not necessary. It will be automatically converted to the Modelica type from the originating OPC UA type. But we once again need to set the node ID type to string ID. And the node ID was level. And again, the namespace is going to be 1. So that's everything you need to do for reading and writing to different node values. So let's validate the model to check that I didn't make any mistakes. And that looks good. Next, we need to set up our model for real-time simulation. So we go to our experiment setup. And it doesn't make sense to have an end time, so we will set this to infinity, the stop time. And we will also check the synchronize with real time to true. And that's everything set up. Now we will switch to Simulation Center, the environment for running simulations in System Modeler. And here I have the pre-built simulation for the plant model that I will start. That will start writing data to the OPC UA server. And we can look at the current tank level when it's running. So no one is providing any reference. So the reference is set to 0, and therefore the tank is empty. So if we build and simulate our model that we created, the read and write, we suddenly start seeing changes to the tank level, which is because we are now providing a reference input. So if we create a new plot and look in our model, so we had the write ref that writes the reference signal for the controller. And we can plot the U variable there, which is the input to it. We can see the signal that we provide to the controller. So we can see the pulse train here alternating between 0.5 and 0.25. And here we have the read block that we named read level. And if we look at the output Y from that, we could see what result we get from the simulated plant model. And here we see that when the reference starts to go up to 0.5, the tank starts to fill up and we have some overshot before the regulator gets it to the reference value. And then when the reference changes back to 0.25, the controller regulates it back to that level, and so on. So that's how easy it is to build a simple model for reading and writing data to an OPC UA server. So let me stop these so I don't consume too much CPU. And switch back to the presentation. So to summarize, the Wolfram OPC UA library is built on an open and evolving standard that provides secure and real-time data exchange with a wide variety of physical systems. It enables applications like data analytics, software in the loop and hardware in the loop testing, and operating training, and much more. And now we have time for some questions and
Yes. Thanks, Otto. In the meanwhile, Robs, can you help us with the last poll for today? Yes. Right, Otto, we have had some questions from the audience, and I also have some questions for you, if you don't mind.
Yep.
So, Robs, are we done with the poll? Can we move on, or?
Yeah, the poll is open in Kit. People are starting to answer it. I will let you know. Well, we have some answers right now.
Yes.
Yeah, I don't know if you want to comment on that or keep with the question.
Uh, yes, so this is interesting. Um, this is interesting. Dashboards and user interfaces. Um, yeah. Uh, okay, Atus. So the first question: how can I download the OPC UA library? Like, how can I access the library?
Yeah, so if one goes to the Wolfram System Modeler product page, we have a section libraries here with model libraries that leads to the System Modeler Modelica library store. And here we have the OPC UA library that is available for free download.
Right, and that is available for all platforms.
Yes.
Yes. The second question that we had was, okay, once I have downloaded the library, we have a question like, is there a user manual for the library? Uh,
Yeah, so the user library or the library comes with a getting started guide that is built into the library that basically walks you through creating creating an example that writes some data to a server and then some part that reads it back and writes it to a different server. So it's a multi-server scenario, and it goes through this in steps.
yes.
And there is, of course, also built-in documentation, not of the tutorial kind, but for each of the component in the libraries, there is documentation.
Yes. Uh, then we had a question on what are you aware of different industries where the OPC UA standard is used?
Yeah, I mean, it is heavily used in the automation industry. Industrial PLC equipment usually have this kind of service built in, or could be connected to OPC UA servers.
Right. And I guess it's also prominently used in oil and gas and process industry.
Yeah, and
Right?
it's becoming more popular for like building automation and various equipment monitoring, like mining equipment or uh, laser cutters and all sorts of things. Even vending machines have their own companion standard.
Yes. Uh, uh, right. Okay. Uh, then in your demo, you were referring to a tank model that we were controlling. Do you have that model with you so you can have a look?
Yeah, we can have a look. Um,
So basically, in this model, you were writing, you're giving a pulse input, you're defining the reference for the tank level, and you were sending it to the client. And that reference was used by the tank model, right?
yeah, that's correct. And then we read back the level that the tank model produced.
Can you open the tank model, please?
So the tank model was this model, which is
Right,
it has a source that is continuously providing a flow of liquid to the tank,
right,
and then it has a PI control. It has some outflow port that is controlled by the PI controller,
right,
and it takes a reference value as an input and provides a level as an output. And then to connect this model to the OPC UA server, we actually used this model. So
right.
we had the tank model. We
Yes,
fed it with the signals that it reads from the OPC UA server,
right,
and we write back the current tank level.
right, right. So also, as you mentioned at the start of your presentation, this is a new version of the OPC UA library. We might have some users who we have tried it with the older version. Is this new version compatible with the older version, or it is a small change that someone has to do if they want to upgrade to this.
Yeah, unfortunately, it's not backwards compatible, so you will have to do a bit of manual changes to your model for it to work with the new library. It has a lot of similarities, so it's fairly easy, and usually you don't build up maybe the parts you create of the OPC UA with the OPC UA library isn't that complex, so it's usually not that difficult to recreate them.
Yes. Yes.
But in contrast to the old library, this is way more efficient because here it groups all the read and write requests into a single request.
Yes, and compared to the older version, now it's secure as you can add your own certificates, and it's scalable, right?
Yeah.
Yes, that you mentioned. Uh, one keyword that you had mentioned twice or thrice during the presentation is Modelica. So some users might not be aware of Modelica. So can you just briefly explain what that is?
Yeah, so it's an acausal modeling language that is a foundation for the system modeler. And it's also connected with a graphical part. So underlying in this, we have it is textual code that you can look at, but you can to your components you can tie graphical representations, and then you can do all your or most of your modeling in a graphical way. So this is the same model, the text representation of the same model, and we can switch back to the graphical view.
Right. We have a question like, do we need to purchase system model application to make control algorithms and dashboards? Uh, yes, it's a different product than the Wolfram language, so uh, I think you have to purchase it. But all the libraries that we mentioned are free to use in System Modeler. Uh, yes. Uh, okay, so we have an interesting question. Like, we have a user who wants to connect everyday appliance to their digital models. Uh, how easy it is to do auto. I can tell you, I was able to use. There is a free OPC UA server that I installed on Raspberry Pi, and I was able to access the GPIO ports from the Raspberry Pi. So possibly, if you can connect to your Raspberry Pi, then you could attach it to your digital models. But also, if you want to add something there.
Yeah, I mean, I would also probably go that route with using a Raspberry Pi for connecting to some appliance and having an OPC UA server on the Raspberry Pi. Another option, if you want to do work with Wolfram products, is to use the model plug library in System Modeler. That allows you to connect to Arduinos, and then you could use that to connect to your appliance, and then use OPC UA library to feed the data to an OPC UA server.
Yes. We have a question. Will you be showing how Mathematica has access to the server data? Uh, do you have any good answer to that, Otto?
No, I don't have any prepared thing that I can show for that, unfortunately.
Right. But if one has to do that, then they have to use the system model simulate function of a current model, and that way they can access the plot in real time. I just don't know. Like, is that the way it should be done?
Yeah, you have to use. I don't remember on the top of my head
WSM,
the
yeah,
function.
WSM real time simulate.
Yeah, exactly. That's the
Yes,
thing you want.
yes. So there is a way using WSM real time simulate that one can access the server data, but with system modeler in between, right?
Yeah,
Right.
exactly. And we have use cases of that where we have used that for creating custom control interfaces in Mathematica for controlling lab setups.
Yes. Uh, yes. Let me see if we have more questions. See. Um, and uh, we have questions like, will can this OPC UA be used for IIoT applications and such?
Yeah, I mean that's one of the application areas. You can have OPC UA servers running in the cloud that you can connect to.
Yes. Yes. Uh, yeah. Thank you, Otto. I think I covered all the questions that were there on the chat. Perhaps, how should people contact us, Otto, like in case they have queries later on when they're trying the product?
Yes, we have the Wolfram community site, and on that we have a thread opened for this webinar where you're free to ask questions if they pop up afterwards, and we will tend to them there.
Yes, and we have got questions like, people want to have similar webinars or on topics where they can connect to industrial sensors. If you have a topic in your mind that you would like us to create a webinar on, please feel free to post in the community thread, and we can see what's possible, and then we will try to have similar webinars in the future as well. Right. We have one last question, Otto. Like, if we don't need a graphics, can we use Mathematica to create code? I mean, I think
If you
the
buy code, mean Modelica code, yes, there are.
yes, uh, yes. I'm not sure if it meant the OPC part as well. If it was intended to use the OPC component from Mathematica without the graphic interface.
But I mean you can still
Yes.
assemble Modelica models from Mathematica, so
Yes. Yes. So
you
you
can
can
use
load.
it.
Yeah, you can load the SMA using the Wolfram. Yes. So you can load the OPCA library using Wolfram language by just doing import of the SMA. And once you have imported the library, then we have functions like create system model and connect system model that can be used to create Modelica models programmatically. So you don't need the graphical interface because Wolfram language comes with a system modeler kernel. Right.
Yes,
Okay.
there could actually be interesting use cases there in that in these information models is specified in an XML format. So potentially you could use Wolfram language to parse that, and then automatically generate Modelica models with the Wolfram language based on that. That matches the information model for your particular equipment.
Right. So when you say information model, what is it, Otto? Like, it's new to me, so I'm just curious.
I mean, it's a way to describe relationships and semantics of your data, how they relate to each other, and so you can create links between. At the basic level, the elements are called nodes in OPC UA, and the node could contain a value or it can contain other nodes, and you can have links between nodes, and the links can be of various types. So it gives you a way to reason, machine reason about your model.
Right. That sounds like a good topic for a community post if you have some time in the future.
Yeah, it's not something I have ever explored extensively, but I think there really is something interesting you could do there.
Yes. Okay, then. I think with that, Otto, we have covered all the questions, and you have nicely pointed out to the community thread where people can ask questions if they have later. Uh, I think with that, we have covered everything, Robs.
Wonderful. Well, many thanks to you, Otto, for leading the session, and to you, Ankit, for helping with the Q&A. And of course, thanks to our kind audience. That's all we have for you today, but please stick around. We have an after-event survey. In fact, let me share that with you right now. Please let us know what you think about this event. Make some suggestions. We will read every comment that you post there. Uh, as mentioned, you can make suggestions about upcoming webinars, system modeler events, or whatever you want to tell us there. We will answer you back as soon as possible. And please note that you will receive a recording of today's webinar along with some other resources that you might find useful. So please take some time to check that email. It was our pleasure to have you